Welcome to The Debate, a show where we explore substantive issues by examining opposing viewpoints on the material before us. Today, we're delving into, well, one of the biggest questions out there, the very origin of our universe. It's a journey into the cosmic past that really pushes our understanding of, well, everything, time, space, existence itself.
Absolutely. And our central question today is this. Given the remarkable observational successes of the Big Bang Theory, should its enduring conceptual mysteries and the, frankly, compelling existence of alternative cosmological models prompt a more critical reevaluation of our understanding of the universe's beginning?
Right, so I'll be making the case for the Big Bang Theory, highlighting its robustness and its just incredible ability to explain where the universe came from and how it evolved.
And I'll be taking the other side, challenging the completeness of the Big Bang Theory. I want to focus on those, persistent, unresolved questions, the things that still keep cosmologists thinking, and maybe explore the potential insights we might get from looking at alternative models.
Okay, so the Big Bang Theory. At its heart, it's our most powerful and, I think, widely accepted story of cosmic origins. It paints this picture, right? Our universe popping out of an unbelievably hot, dense state, and then just starting this rapid expansion, about 13.8 billion years ago. The beauty of it really lies in its ability not just to describe, but to actually predict key observations that have shaped modern cosmology. Think about Edwin Hubble back in the 1920s. His groundbreaking observations first showed that galaxies aren't just sitting there. They're actually rushing away from each other. And their speed is directly proportional to their distance. So it wasn't a static picture. It was dynamic, expanding. Then fast forward to 1965. You get this, honestly, accidental discovery, but it was absolutely crucial. The cosmic microwave background, the CMB. You can kind of imagine it as the universe's oldest light, yeah? A faint, really uniform microwave glow filling all of space. It's literally the afterglow of the Big Bang. It's a relic from when the universe cooled down enough for light to finally travel freely. And its thermal spectrum? It's exactly what the theory predicted for the cooling embers of that early hot, dense state.
Okay.
And beyond that, the theory nails the predictions for the amounts of light elements. That sort of enduring 3-to-1 ratio of hydrogen to helium we see everywhere. That was forged in this brief, intense period, maybe the first 20 minutes right after the Big Bang. Primary nucleosynthesis, they call it, like a cosmic forge making the first building blocks. And the theory gives us a whole timeline, too. From this insanely rapid burst of cosmic inflation that smoothed things out early on, through making fundamental particles, and eventually the atoms that make up, well, us and everything else. And now, with tools like the James Webb Space Telescope, we're actually seeing galaxies that formed way back, maybe 13.6 billion years ago. It gives us these direct glimpses into the early universe, and it really powerfully reinforces the whole Big Bang narrative.
Okay, look, I absolutely agree. The empirical successes you've laid out, they are monumental. There's no question. And it's completely clear why the Big Bang Theory holds such sway in the scientific community. However, and this is a big however, for all its explanatory power, I think it's just as crucial to, cast a critical eye on its limitations, the inherent ones, and the, frankly, profound conceptual challenges that are still there. The theory, yeah, it's triumphed in many ways, but it still struggles with some fundamental questions. It often leaves us right at the edge of what we can even really conceive. Take, for example, that perennial question, what came before? The Big Bang idea posits that time and space themselves originated with this event. So asking what was before becomes, well, almost scientifically meaningless, right? Like asking what's north of the North Pole. But let's be honest, for many people, that conceptual boundary just feels deeply unsatisfying. It sort of prompts this search for models that maybe allow for a continuous existence in time, a universe that perhaps didn't have an absolute start.
I see what you mean, yeah.
Then there's the initial state itself, the nature of the singularity, this completely enigmatic, infinitely dense point where basically all our current physics just breaks down. The Big Bang tells us what happened after that moment, but it's incredibly speculative about the conditions or the mechanisms that actually started it. It's like hitting a conceptual wall again and again.
Right.
And finally, you have this expansion into what? Paradox. If space itself is expanding, our intuition just screams, what's it expanding into? Now, the concept says there's no external void. I get that. But the implications for the universe's overall shape, is it finite, infinite, flat, curved? These present incredibly complex paradoxes for our theories, which, let's face it, often rely on having a finite amount of energy to work with. These unresolved issues, they are just small details. They're deep philosophical and scientific challenges, and they genuinely open the door for alternatives. Think about the steady-state theory. Mostly superseded now, sure, but it offered a universe with no beginning or end, where new matter just pops up to keep density constant. Or maybe the cyclic model, the big bounce idea, that proposes an infinite series of expansions and contractions, which neatly avoids a single starting point. And there are other hypotheses too, like plasma cosmology, suggesting different forces dominate universe formation. It just highlights that the Big Bang, yeah, it's dominant, but it might not be the final word. It might not be the only possible explanation.
Those are definitely compelling points, and they tap into that very human need for a complete story, right? An unbroken narrative of where things came from. But let's dig into that before question a bit more, because I think the Big Bang framework, especially when you include cosmic inflation, actually offers a slightly more nuanced view than just, hitting a brick wall. The hot Big Bang, the part we usually focus on, with matter and radiation that was likely preceded by cosmic inflation. This incredibly rapid, almost instantaneous, exponential expansion happened before the universe as we normally think of it, before matter even really formed. So this implies that even within the Big Bang model itself, there was a kind of time before the universe of atoms and stars. It shows the theory can actually model processes beyond just simple matter formation. And when you talk about time, well, we really have to see it as fundamentally linked to the universe's existence. It's not some pre-existing stage, right? It's a dimension of space-time itself, just like length, width, and height. So asking what was before the actual fabric of existence, before space-time itself came into being, it really could be seen as a category error, within our current physics anyway. It's asking a question that might not have an answer in the way we normally understand before and after. It kind of forces us to rethink what causality and existence even mean at that scale.
I understand the elegance of framing time that way, as an emergent property. And cosmic inflation, yeah, it's a powerful idea, solves a lot of problems with uniformity and stuff, but it still feels to me like we're kind of sidestepping the fundamental question, the ultimate origin, that true first cause, the idea that time just sort of stops existing at some point or just springs into being with one event. That remains a really profound conceptual hurdle, I think, for many. It feels like we keep pushing the problem further back, without ever really tackling it head on.
Okay.
For me, the appeal of models like the cyclic universe is precisely that continuity. The cyclic model, for instance, it's not always just an infinite loop. Sometimes it involves really advanced ideas, maybe from string theory or brain cosmology. Maybe our universe is like one membrane hitting another, generating a new bounce, providing a physical mechanism for a beginningless existence. This framework suggests, well, maybe there is no absolute beginning to time, just these transitions between different cosmic states. It feels like a potentially more, elegant solution to the before question, even if, we lack direct observational proof right now. It offers a more holistic view, maybe, where fundamental constants or laws could even evolve across cycles instead of just appearing out of nowhere. It doesn't tell us to stop asking why, which I think is important.
That's a really interesting take on continuity and the potential mechanisms of a cyclic universe. I can definitely see the philosophical appeal, of a universe without that single starting point. However, and this is where I have to push back a bit, the Big Bang Theory's real strength and the reason it's still our main model boils down to that incredible predictive power. It's been validated by observation again and again, in ways that these alternative models just frankly struggle to match. Take the cosmic microwave background again. It's not just something we observe. Its incredible uniformity, its precise thermal spectrum that is exactly what the theory predicts as the leftover heat from that early hot, dense phase. It's not just an interpretation, it's a direct consequence of the model's physics. Similarly, predicting the light element abundances accurately, that specific ratio of hydrogen, helium, a bit of lithium, all cooked up in that early nucleosynthesis, that just further underscores its empirical success. And yeah, okay, new telescopes like JWST are showing galaxies maybe forming a bit earlier than we initially thought, but these look like refinements within the Big Bang framework. They're pushing our understanding of how structure is formed, sure, but they're not overturning the core theory. Science is about refining models with new data, right? And the Big Bang has proven remarkably adaptable, incredibly robust in incorporating these new findings. That says something about its foundational strength. We're not just seeing things, we're confirming predictions.
I agree. I agree entirely. The predictive power, especially with the CMB and the elements, it's huge. It really is a testament to the scientific method. However, that very success also kind of throws certain inconsistencies we're now seeing into sharper relief, things that maybe point to the limitations of the standard model. For example, what about this whole crisis in cosmology around the Hubble constant? We have different ways of measuring the universe's expansion rate, and they're giving us conflicting values. It's a persistent discrepancy, and it suggests there might be a fundamental inconsistency in our standard model. It's not just a tiny refinement, it's a real challenge to a key parameter of the whole universe. It suggests maybe there's some physics missing from our current picture.
That's a fair point about the Hubble tension, definitely.
And furthermore, while the CMB is absolutely real, no one disputes that, there have been alternative interpretations proposed. Plasma cosmology, for instance. It suggests that maybe large-scale structures aren't just formed by gravity, but also by huge electric currents and magnetic fields in cosmic plasma. This offers a different explanation for some observed phenomena, maybe even certain features in the CMB itself. Now, these ideas aren't nearly as widely accepted, I grant you that, but they do highlight that how we interpret evidence isn't always straightforward. Sometimes these anomalies are exactly what pushes towards deeper understanding. The fact remains, the Big Bang is still a theory. It's based heavily on complex math, on models, not on, a direct snapshot of the initial moment. And that means we have to stay open to other frameworks, especially when we keep running into persistent anomalies that might just be pointing towards a deeper truth we haven't found yet.
You raise a valid point about the Hubble tension. It's definitely a hot topic, and it challenges our precision cosmology. But let's switch gears slightly, back to the nature of space itself, because I think really getting your head around space expanding rather than expanding into something is just fundamental to grasping the Big Bang. It messes with our everyday intuition for sure.
Yeah, it does.
Imagine not just dots on a balloon surface moving apart, but imagine the actual rubber of the balloon itself being created as it inflates. That's kind of how we need to think about space. It's not expanding into some pre-existing void out there. It's the fabric of reality itself getting bigger, everywhere, all at once. And it carries the galaxies along with it. There's no center point to the expansion, and it looks the same in all directions, which is beautifully backed up by how incredibly uniform the CMB is. This spatial expansion comes right out of Einstein's general relativity. It's a core idea, and it's how we can understand having an observable universe that's finite in age, but could potentially be infinite in size, all without needing some outside for it to expand into. The idea that space itself is being created as it expands sort of bypasses that philosophical need for an outside, letting the models be self-contained.
I appreciate you clarifying that. The spatial expansion idea and the balloon analogy, yeah, it's helpful for picturing it. But I still find myself wrestling with the implications, particularly energetically and structurally, of an infinite expanding space within the Big Bang model. If space is truly infinite and expanding uniformly, doesn't that imply an infinite amount of matter and energy? Which then kind of clashes with many cosmological theories that seem to need a finite energy budget for the math to work out to avoid certain paradoxes. Now, okay, a spherical or closed universe could maybe solve some of that. You could theoretically travel and end up back where you started. But our observations, they keep telling us the universe looks remarkably flat as far as we can measure. So a simple spherical model doesn't seem to fit the data perfectly either.
Right. The flatness observation is key.
So this leaves us with these fundamental uncertainties about the universe's ultimate shape, its total contents. And if space is being created, like you said, what is the fundamental nothing it's arising from? That remains this incredibly deep philosophical and scientific challenge that the Big Bang Theory, at least in its current form, doesn't fully resolve. It basically asks us to accept the creation of, well, everything from effectively nothing. And while it's elegant in describing what's happening, it still leaves this profound gap in explaining why it's happening or what the ultimate cosmic boundaries or lack thereof really mean for reality. These aren't minor points, they're fundamental questions about existence itself, the very questions that alternative models are trying to tackle.
So as we sort of wrap up this fascinating discussion, it really seems clear that the Big Bang Theory, despite its grand sweep and the mysteries it holds, it does remain our most powerful story of cosmic origins. That bedrock of observational evidence, the expanding universe, the CMB, the precise element abundances, it continues to provide the most comprehensive, the most robust framework we have for understanding where the universe came from and how it evolved. Yeah, it definitely presents these profound mysteries, challenges our definitions of time and space, for sure. But it gives us a consistent, adaptable narrative. It lets us probe the universe's deep past, predict its future, and it's constantly being refined by incredible research and new data. It really is our strongest scientific explanation for the universe we see.
And while I absolutely acknowledge that explanatory power, the empirical successes of the Big Bang Theory, it's just as important, I think, to keep highlighting that significant conceptual gaps, these unaddressed questions, they do persist. The nature of before the Big Bang, the fundamental origin of that initial state, the ultimate size and shape of the universe, these are still subjects of intense debate. And there are fertile ground for alternative models. For me, actually, these persistent mysteries, they aren't really weaknesses. They're more like a testament to how much more there is to figure out. They're a constant invitation to push the boundaries of what we think we know. These challenges just underscore that our journey to really comprehend the universe's beginning is far from over. And that, a healthy dose of scientific skepticism alongside a willingness to explore different ideas is absolutely essential if we want to make real progress.
Indeed. Our exploration today really highlights the incredible complexity, doesn't it, and the ongoing scientific effort to understand our universe. We hope it invites all of you listening to continue your own exploration of these truly profound questions. Thank you for joining us on The Debate.